Alright, so this is one of the more important videos. In this video, we are going to be concluding the theoretical part of heat transfer and work. Not heat transfer, my bad. Heat and work. And after this, we have only the tutorial left where we are going to be looking at the questions. For this chapter, you cannot skip the tutorial at all. You have to do the questions because only this theoretical part will get you nowhere, right? So, with that being said, let's begin. And we're going to be looking at moving boundary work, also called P-dV work. So, let us say that we have a piston that has three weights on top, and here we have something. Now this piston is in equilibrium, so that means there is an internal pressure. Now if we remove one of the weights, what is going to happen? There's going to be some expansion by a distance dx. So we can say that the small work done will be the force that was exerted by this into that distance dx. This comes from physics. Remember, work is force into displacement, right? Force into displacement equals work, right? And since pressure is force upon area, we can say equals to P into A dx. Now, I want you to focus on this A dx term. What is this A dx term? See, this is our piston when seen from the top, right? And it has some area of A. Now, if we multiply this area by the length that it moves, we will get a volume, or the small volume by which the piston moves. So that means P-dV, right? And if we integrate both sides, we get equals to integral P-dV, which implies work done from 1 to 2 equals to P-dV. Right? And if we represent this process on a graph, it will look something like this. The pressure will decrease while the volume increases. This is 1, this is 2. And the area under this graph will give us work done from 1 to 2. So that was the basic definition of work, of P-dV work, how it is defined and where we got this formula from. Derivation is not that important, keep this formula in mind. Now, we're going to be looking at the various processes by which this work can occur. We have isochoric, V equals constant, which means dV equals to 0, which means work done is 0. We have isobaric process, where P equals to constant, which implies work done from 1 to 2. That is, we can take it out of integral because it is a constant, right? I'm just going to go through this very briefly because we've already done this. P delta V. Then we have isothermal process. Temperature is constant. For this, the formula is P1 V1 ln V2 by V1, P1 V1 ln P1 by P2, or nRT ln V2 by V1 in case of ideal gas. Then we have the polytropic process, where P into V to the power X is constant, where T V to the power X minus 1 is constant. And similarly, you can get one more from PV equals to MRT relations. Just substitute and replace. However, I do find it to remember all of the three equations of polytropic process to be useful. On a graph, a polytropic process will look like this. This is just some extra info, you don't need to remember it. This is for x equals 1, x equals to 1.4, x equals to 0, and x equals to infinity. This is just a graph of the polytropic process, don't need to remember it. And work is P2V2 minus P1V1 upon 1 minus x, or n or delta t by 1 minus x, where x is not equals to 1. So that was all the processes that we have seen so far. After this, we're just going to solve a couple of quick questions, right? Let's go through the question. A piston cylinder device contains 0.15 kg of air initially at 2 megapascal and 350 degrees Celsius. Okay, let us draw our piston cylinder device. So this is state 1, air, P1 2000 kilopascal, T1 350 degrees Celsius. Keep doing this as you read the question, because then the room for errors is much less, right? The air is first expanded isothermally to 500 kilopascal. Okay, expansion process is occurring. Piston has moved up isothermally. Okay, we don't know the P2. Then the T2 is constant because it is isothermal, state 2, and then compressed polytropically with a polytropic exponent of 1.2. So it looks something like this now. And we don't know the P3 and the T3 and the V3 as well. Oh, in fact, we do have some relation of the P3 with polytropic exponent of 1.2 to the initial pressure. Okay, so it goes back to the initial pressure, P1 of 2000 kilopascal. And then finally compressed at constant pressure to the initial state. And at this P equals to constant to the initial state. So we go back here, and T4 we don't know what it will be. Take R for air as 287 joule per kilogram Kelvin. This is also given in your thermotables. If you don't have it given in the question, remember you can always refer to the thermotables to find the values of R and other constants, right? Draw the cycle in PV diagram. Determine boundary work for each process. Determine net work for the cycle. Okay, we're going to start with part B. Part A, obviously, anyone can do. From 1 to 2, that is isothermal process. We know the formula nRT ln V2 by V1, or nRT ln P1 by P2. Substituting all of the values, MRT, we use MRT in thermodynamics, not M, not N. We get into 287 into 350 plus 273. I want you to answer why we are doing this. Ln P1 by P2. Okay, so we don't know P2. Luckily for us, it is given that it is air, right? So we can say that it can be assumed to be an ideal gas. In this question, they want you to assume it to be ideal gas because otherwise you won't be able to move ahead with it, right? So we have PV equals to mRT, and we know that the temperature is constant. The mass of the gas will also remain constant because there is no mass exchange. It is only being compressed or expanded inside the tank, right? So the mass is constant and R is obviously a constant. So that means P1V1 equals to P2T2. P2V2, not T2. Wait, are we given? Oh yeah, we are given P2. P2 is 500 kilopascals. Okay, so no need to do the whole ideal gas thing. Sorry, my bad. Right. And with this 2000 by 500, and we get W from 1 2 to be 37180.6227 joule. Now from 2 to 3, it is a polytropic process with polytropic exponent of 1.2. The formula is P2V2 minus P1V1 by 1 minus x, or NR mR delta T by 1 minus x. So to solve this, how will we solve this? We do not know V and we do not know T as well. So we can find either of those two because we know the pressures, right? So we can find V and then use P1V1 minus P2V2. But then we'll have to find the volume at this state also. So I think it is better to use the delta T because that way we will only have to calculate one variable, which is T3. So for polytropic, we know that P to the power 1 minus x into T to the power x is constant, which implies 500 to the power minus 0.2 into 623. Why is this 623? I want you to answer yourself. Into 1.2 equals to 2000 to the power minus 0.2 into T2 to the power 1.2. Upon solving this for T2, you will get T2 to be 784.93 Kelvin. Now, substitute all of the values here and get the answer. After you have done the same, for this process, the 3 to 4 process, that is for 3 to 4, pressure is constant. That is given to us to be 2000 kilopascal. So work done is integral P-dV is P delta V. Because pressure is constant, we can take it out of the integration sign, right? So delta V can be calculated. From here, you can calculate the volume at the initial state. From PV की power x is constant, you can calculate all of the other volumes required, plug them into this formula and get the answer. As for your graph, it will look something like this. Why is that? Let me explain. One to two, it is an isothermal process, right? Isothermal process will look something like this, right? PV equals to mRT. So P and V are inversely related, so we'll get something like a hyperpolar graph, right? Anyways, also if you don't know this, you know that this is how the isothermal graph looks. Then 2 to 3, we have a polytropic process. Won't exactly be a straight line, it'll be something like this. And then 3 to 1 or 4 is constant pressure, so pressure remains constant. So that was it for this lecture. I hope you understood what I want you to focus on in this chapter, that is the questions. So after this we're going to be moving on to the tutorials. I don't know how many questions we have in this tutorial, but I would imagine it is a significant amount. So it's either going to be one really long video, or it's either going to be several short videos. Right, with that being said, let's move on to the tutorials.